Okay, all right. Hey, good afternoon, everyone. We're delighted to have Peter Armitage from Johns Hopkins to give a talk today on the Ising model of ferromagnetism. Peter actually got a degree from here. He turned in his thesis exactly 20 years ago, October 2001. And so he actually won the Macmillan Prize for his thesis work, and he's since then his research is taking a much better turn, and started using and developing specialized technique in the terahertz frequency regime to investigate quantum materials. Over the last 15 years, his group has become the world leader in application of terahertz spectroscopy on quantum materials. His research accomplishment includes the demonstration of the quantized magneto-electron response in topological insulators, i.e. the so-called axion electrodynamics, which was first formulated by colleagues here, actually Xiaoliang Qi, Taylor Hughes, and Xiuqing Zhang. This is the quantized response functions that define the topological insulators in much the same way as the quantized Hall resistance characterized the quantum Hall effect. He won the 2016 Genzel Prize for the development and application of low-frequency electrodynamic probes to quantum correlated materials. Now his research continues on superconductivity, topological matter, and the subject of this talk, quantum magnetism. Peter, the floor is yours.
Okay. Well, thank you. Thank you so much, CX. Yeah, it's a great pleasure to give a talk, but of course, you know, one of the minor tragedies of the era is that I can't right now come out and visit you in person. Coming and visiting Stanford and talking to friends and colleagues is it's one of my always favorite things to do. So perhaps maybe in the springtime. So today's talk is, I'm going to tell you about the best material realization of the Ising model. This is a material called cobalt niobate, cobalt niobium 206, and experiments that my group has done on it. I hope telling you about a particular material is not going to be considered too prosaic for this kind of general audience. And I want to do a few things in this talk. I'm going to tell you about the Ising model. And it has, of course, been at the forefront of statistical mechanics and quantum mechanics for over 90 years. I'm also going to tell you about the history of the Ising model and Ernst Ising and some of the small contributions that I've made to the history of this. I think that this talk and the subject is interesting for a general audience because the historical developments of the Ising model, or Ising's model, I think it's fair to say show a disregard for traditional academic boundaries. Physics, metallurgy, mathematics have all been involved. And of course, some of the most recent applications of Ising's model have been to biology. The most striking success in the theory of the Ising model involves such challenging mathematics that it stumped all the physicists who had attempted to solve it, and finally it had to be solved by a chemist, albeit one of particular mathematical capacity. When we look at a quantum version of it, it's the simplest case we have of quantum criticality, an aspect which is still at the forefront of condensed matter physics. And it's amazing, I think, that in a system as simple as a one-dimensional chain, analogies to phenomena and mathematical structures, as diverse as quark confinement, quantum number fractionalization, Majorana fermions, Airy functions, 248-dimensional Lie algebras can all be found. I'm going to tell you about the research we've done on this particular material system. But if I have one real goal today, it's to give you a feeling how physicists like myself who are interested in materials and how complex phenomena is realized by them, how we can realize simple Hamiltonians in real systems, in real materials. And of course, it's challenging to look for simplicity and beauty in something that comes to you essentially as a nondescript lump of what might actually start its life as a rock in the ground. So there's this material, cobalt niobate, that I spoke of, and that's it in natural form. It was first discovered as a mineral, discovered in a Pilgrim Puritan farmer in 1600s in Essex, Connecticut. Columbite for Columbus, meaning having to do with the New World. This is the crystal structure here. When we grow it in a traveling solvent floating zone furnace at Johns Hopkins, we grow it, let's say, with higher purity than it's grown mineral is an igneous rock, so we grow it with higher purity, let's say, than the volcano that grew the igneous rock originally. But we grow it with higher purity, but actually the crystals are smaller, and that's the crystal structure right there. I'm going to talk about these aspects as I go. Before I do, let me make kind of thank the various people who made the work possible. First and foremost, my former postdoc, Chris Morris, my colleague Oleg Chernyshov, colleague Tyrell McQueen, long-term collaborator Bob Kava from Princeton, colleague Syed Kupaya. I've had a wonderful collaboration with Ribu Call at the University of Kentucky, which the end of the talk today, the work that I'll tell you about, the twisted Kitaev chain and Cramer's Vania duality. This came out actually at the very last colloquium that I gave before everything shut down in February of last year. I was at University of Kentucky giving this talk, and at the end of the talk, Ribu and I got to discussing, and a very nice paper came out of that. Anirban Ghosh is a former student. Jason Krazan is a student of Kava's. My former postdoc, Rolando Valdez Aguilar, who's now assistant professor at Ohio State. Ribu's former student, Nishita Desai. Collaboration with Thomas Room and various people at the National Institute for Chemical and Physics, Biophysics in Estonia, and then a collaboration with Sabir Sachdev on some theoretical aspects of this as well. So in the talk today, I'm going to tell you about the what and why of the Ising model. I'll tell you about the history of the Ising model. I'll tell you about Ernst Ising and beyond. I'll tell you about this material, cobalt niobate, which is best realization of Ising's model, if you will, and then various experiments, on cobalt niobium 206 and zero magnetic field, where we have evidence for what we might call meson bound states at low temperature. I will tell you about the work that we've done, the most recent work we've done, where we take this chain, this 1D chain system, and tune it through what is probably the simplest realization of a quantum critical point, an Ising chain and transverse magnetic field, and show the interesting stuff that comes out of that, including the so-called Cramer's Vania duality and evidence for Kitaev interactions in these chains and this kind of thing. Okay, so there it is. This is its simplest nearest neighbor case in one dimension. We have two degenerate ground states. The spins can be up or the spins can be down. And we know that in one dimension, only zero temperature has long range order, so a finite magnetization. In fact, in his original paper, Ising argued that the same thing would be true for higher dimensional cases. And now, of course, we know that's not the case. Higher dimensional 2D, 3D systems have finite temperature phase transitions. There he is, and there is his thesis, Ernst Ising, 1925. And one only has to look at the original paper to know that the problem was given to him by Lenz, his thesis advisor in Hamburg. Many authors call it the Lenz-Ising model. In fact, even Ising himself called it the Lenz-Ising model. I call it the Ising model for just the simple reason it makes my story better. Ising intended this model to be a good microscopic model to explain ferromagnetism, and it's not that. It's, let's say, both less than that and more than that. 1924, Ernst published his thesis. In 1925, published his only scientific paper. The 1928, Heisenberg cited this work, and sometime later, Pauli, using at that time the very new quantum mechanics, quantized Ising's model. I think it's fair to say that the history of the Ising model is long and winding, and complete results were long in coming. But even when they came, I think it's fair to say that the recognized significance of them, for instance, the idea of universal aspects to phase transitions, this took much longer. And I think it shows that there's really more to physics than just solving physical problems. One must realize how some result fits into a general context. And we might recognize physics now as, let's say, the search for universality, the search for universal phenomena. But perhaps this wasn't always the case. So the problem that Lenz gave to Ising had two parts, and both parts were impossible. So, very good thesis advisor. So first, Ising had to derive a model for the interaction of the particular magnetic unit. In this case, we would recognize it as spin, that preferred alignment. This is, of course, a problem which belonged to the just invented and at that time underdeveloped quantum mechanics. We refer to this interaction now as super exchange. The second part was that he had to calculate analytically the 3D macroscopic magnetization with the methods of statistical mechanics. So both of these problems, of course, were far too big for Ising. And the first had to wait at least until the 1950s, where super exchange was first discussed. This was done by John Goodenough, who won a Nobel Prize some years ago for chemistry. This was done in the 1950s. And the second had to wait for Onsager in 1941 and 1942 to solve the two-dimensional case. And of course, the three-dimensional case is still not solved. So Ising had to restrict himself to a much simpler version. He had to assume some kind of interaction for the first part, and then he had to restrict himself to one dimension for the second. And so 1D, Ising solved the 1D model exactly, and he got the partition function and showed that there's no singularity in one dimension. Related calculation is, of course, done by most undergrads in their first statistical mechanics course. This is from that first paper. It's a plot, perhaps in an unfamiliar way to you, but this is a plot of the magnetization. You can see in the original German. Again, undergrads typically do this by the method of direct summation in a first statistical mechanics course. And that's a plot here of the heat capacity in blue as a function of temperature, and the energy per spin as a function of temperature. And Ising correctly noted that these curves were smooth. They have no non-analyticities in them at all. And there would be no phase transition in one dimension. And then he had some particular argument that the same thing would be true in, let's say, 2 dimensions and 3 dimensions, and then hence that there's no phase transition at all. And that's wrong. Of course, there is a phase transition in higher dimensions. At the time where he was in Hamburg, and Hamburg was a hotbed for this kind of thing. Pauli had just accepted a position there. Also present in Hamburg at the time were Stern and Gerlach doing their famous experiment. And Ising intended his model as a description of ferromagnetism. And as the model didn't show ferromagnetism, I think it was a failure by that standard. And that's certainly how Ising considered it. So you can see in this 1967 letter to historian of science Brush, Ising wrote, "I discussed the results of my paper widely with Professor Lenz and with Dr. Wolfgang Pauli, who was at that time teaching in Hamburg. There was some disappointment that the linear model did not show the expected ferromagnetic properties." So this disappointment was in part what eventually motivated Ising to leave research. But the general idea that a phase transition was not found was important too. Of course, phase transitions have been noticed since the early days of physics, since they've been noticed since the early days of people, water freezing to ice. And a phase transition, something non-analytic, happens typically as a function of temperature. And what people at the time didn't realize, even in as late as the 1930s, they didn't realize that the thermodynamic limit was essential. And some thought that something beyond conventional statistical mechanics, as understood by people like Gibbs and Boltzmann, was going to be necessary to describe phase transitions. Even as late as 1937, people like Sommerfeld, who were saying that a partition function could only represent a single phase of matter. Each state of matter had its own partition function. And the argument was essentially that all thermodynamic information is encoded in a partition function, and partition functions were sums of exponentials, which are analytic functions, and the sums of analytic functions couldn't have any non-analyticities in them. And so, of course, what wasn't realized was, again, that the thermodynamic limit was essential in this, and that an infinite sum of analytic functions could have non-analyticities in it. So the fact that Ising showed that there was in one dimension, that there's no phase transition, and then had an argument that claimed that the same thing was true for 2D and 3D, this was highly, I think it's fair to say, highly misleading. And you can see, for instance, these comments of Sommerfeld, who were made almost 12 years later. Of course, we've had our revenge on Mr. Ising. At least here in North America, we almost universally mispronounce his name as Ising, not Ising. So it wasn't until later that the idea to study the Ising model as a model for phase transitions in general caught on. The concept of Ising model as a kind of mathematically interesting object existing independent of any particular approximation for a physical system. This seems to have started in the Cambridge group of Fowler in the 1930s. Anytime, of course, you have a binary variable, you can map it to the Ising model. And in this regard, Piles has an interesting paper in the title of my talk today on Ising's model of ferromagnetism. This comes from Piles's paper. Piles probably regarded the different uses of the Ising model in his work where he discusses things like Bragg and Williams and Beta's theories of alloys, Fowler's theories of what was called the liberation rotation transition. He writes in this paper, as I should put here, these models, these were all physically different, but mathematically equivalent. And so in this regard, he probably regarded these as different uses of the Ising model, not because they stem from the same mechanism or deal with the same physical objects, but they're just mathematically equivalent because they obey the same equations. But you can see in this early work that the idea that's now so prevalent in the study of phase transitions, the notions of universality, fluctuations, critical exponents as a general phenomenon, this is all still missing. In the early 1940s, Onsager proved that the zero field transition exists, an exact model. He gives the partition function. So this is some epochal moment. 1952, Yang gave a formula for the magnetization, but even then, the idea that the Ising model was going to be useful and important was not realized. And I find that the attitude towards these successes are curious, at least from the modern perspective. Yang himself had said about the Ising model that it was not useful because it wasn't realistic, meaning you couldn't describe a ferromagnet with it. And the standard was that people should be making realistic models of ferromagnets. I came across a story of Oppenheimer introducing Yang I think at a Christmas party in the early 50s, and introducing Yang to somebody else and saying that they should come over here and meet Mr. Yang because he had done a, quote, marvelous bit of mathematics. When what Yang had really done was given an exact formula for the spontaneous magnetization in 2 dimensions. He had shown that the critical exponent was 1/8, which is tremendously different from the mean field result. And I think I still find it quite remarkable that a seminal bit of physics like this was discarded as just a quote unquote bit of mathematics. As you go on, it looks like in many cases in these works through the 50s and 60s, the grand significance of all of these things were not realized. And again, Yang in the 50s saying that the Ising model wasn't important because it wasn't realistic. It was only in the 60s and 70s that it was begun to be realized that simple models could be important in their own right, because they get the physics of things like critical exponents right, and things like universality could form. These were people like Wilson and Kadanoff, Fisher, Daum, Whittam, and others. And they realized that the Ising model was important not as a model of ferromagnetism, or even as a, if you say, formal curiosity that many systems could be mapped onto it, but as a model for critical phenomena, generally speaking. If the Ising model could be applied to and got an exact agreement with magnets, liquid gas phase transitions, binary alloys, then it has some realism to it that's not connected to being a good model of any of these things by themselves, but instead a model for universal aspects of phase transitions, something that unites them. This is of course a beautiful thing. So we now understand these are some plots, if you will, for the liquid gas phase transition and the Ising model in 3 dimensions, the critical exponents when you map from one set of variables to another set of variables. There's a correspondence between them. I just noticed there was something coming up in the, I see in the chat. I can't read things in the chat, so if there's something,
just please mute yourself.
Yeah, thanks. So okay, so right, so the point is that universality is something that we recognize now, but took a long time, almost 60 or 70 years to be understood properly, and something in the case of the Ising model. So now, of course, classical and quantum versions of the Ising model everywhere. Anytime you have a binary variable, this is my own rather dog-eared copy of Sabir Sachdev's book on quantum phase transitions. And there, the formalism of quantum phase transitions is built up through looking at the one-dimensional Ising chain in transverse field. Of course, again, the Ising model is everywhere. Of course, in magnets, this is a result by Bach et al. Looking at atomic layer of iron, where you can see that there's something like 36 orders of magnitude in reduced magnetization, and 24 orders of magnitude in reduced temperature, and it fits the exact functional form derived by Onsager for the 2-dimensional Ising model. But, and this is remarkable because despite all the experimental imperfections and homogeneities, non-localized magnetic moments, it all still works. But there is all kinds of other places where we apply the Ising model now, lattice gas models and binary alloys. in Ising models for cancer growth and biological systems. The Ising model has been used for modeling social, racial segregation in American cities. You can even find places where you can use the Ising model and statistical mechanics of it to avoid paying your taxes, an Ising model of so-called tax evasion that you can look up. So for the rest of the talk, what I want to do is turn back the clock on all of this progress. So I want to come back to Ising's original kind of model, if you will, for the one-dimensional Ising chain and ask, can we find a material system which would be a good realization of Ising's model? How do we realize Ising's model in a real material? If you have, let's say it needs to be 1D or quasi 1D, we want it to be spin 1/2, small exchange constants, perhaps, so we can maybe manipulate them with external magnetic fields and push it into different regimes. Ideally, it doesn't have to be, but ideally we like it to be ferromagnetic. We need a strong Ising anisotropy. The spins we want to be either up or down. And ultimately, we're going to be looking at materials. And so it's going to be always an issue, if you will, that we have competing interactions. At the very least, there's things like lattice vibrations, phonons, that can come in. And so we don't want things like phonons to play a principal role. And so it was pointed out some years ago by Radu Koldea that this material here, cobalt niobate, cobalt niobium 206, which we call column white, is perhaps the best material realization of Ising's model. As I mentioned, it is first discovered as a mineral, and this is it in the Natural History Museum in New York City. This is the crystal structure. It's this kind of zigzag chain of cobalt ions, which are edge-sharing tetrahedra. It's of course an igneous rock, and we look at the pure form, which we make in traveling solvent floating zone furnace at Johns Hopkins. Please turn your microphones off. Mute yourself, please. This is the crystal structure here with the zigzag chain that can be seen as such. So let's look to see how do we realize Ising's model in this. So there's the cobalt ions surrounded by oxygen octahedra. So this is a D7 cobalt +2 ion in the octahedral crystal field. This has what you might call T2G5 EG2 configuration. This has it's a high spin S = 3/2. It has effective L = 1 moments, but this gives you effective uniaxial pseudospin that we can see as an effective J ±1/2. And so let's get rid of the oxygen ions and perhaps maybe pull this thing straight. The zigzag is not going to be very important for our current purposes. Put the spins in the material itself. The spins actually sit at some funny 31-degree angle to the crystal structure, the kind of naive crystal structures, but we can just do a coordinate transformation to kind of set them straight. Let's get rid of the cobalt ions altogether. And there's our Ising model. Okay, excitations in this system are spin flips, right? We can flip spins up, flip spins down. The material, of course, itself is more complicated than that. And for some of the aspects, we're going to have to worry about these details. Plotted here on the left, on the right, lower right side, is a plot of the heat capacity versus temperature for cobalt niobate, our material, and then also a non-magnetic analog, zinc niobate. And so you can see the zinc non-magnetic analog, the heat capacity just kind of comes down as you expect for an insulator. But in cobalt niobate, about 20 Kelvin, it starts to deviate significantly from the non-magnetic analog. And then there's a peak here and a shoulder. There's a peak here and a shoulder there. And these are two phase transitions that happen as a result of ordering and interactions with the other chains. So we have these ferromagnetic chains, which then have a very weak interaction with their neighbors, which is actually anti-ferromagnetic, and it goes through a series of two phase transitions where the lowest temperature state is actually an anti-ferromagnet, with ferro chains anti-ferromagnetically correlated with their neighbors. This is kind of a bit of a cartoon of what's going on right there. But it's important to note that the material really has almost, let's call it quasi long-range order as we cool down. The correlations become very, very long-lived. And along the chains at 3 Kelvin, one can estimate that the correlation length along the ferro chain is something like 100 lattice constants. So it doesn't order, of course, till 0 temperature in a 1D chain. There's finite temperature order that comes as a result of these higher dimensional interactions, but it's almost ordered at 3 Kelvin. 100 lattice constants is pretty good. Now, one of the things that I said we needed was strong Ising anisotropy. This doesn't show that precisely, but it does show it kind of in a heuristic fashion, the strong magnetic anisotropy. So this is a plot of the magnetization as a function of temperature as we cool down in small fields pointing in different directions. The spins themselves sit in the AC direction, AC plane. And if we cool in a small field with field along A or along C, we can get a small canting in this direction. You can see the magnetization can become quite appreciable. But if we put the magnetic field in the B direction, which is the hard direction, it doesn't want to magnetize at all, even as we cool down. Eventually, we are going to put the field in the B direction. That's the transverse direction. That's going to be important for various things we're also going to talk about. But for right now, this shows strong anisotropy. Now, there's our Ising chain, right? And that's the simple Hamiltonian. We're generally going to want to add some other terms to the Hamiltonian. And so, for instance, if we do put a field in the SX direction, in the X direction, this is what that operator looks like, and it looks like a spin flip. I didn't bother normalizing anything here, but if we put a field in the X direction, this is going to take one of the spin up terms, the spin ups, and turn it to spin down, okay? Now, in the real material, as I said, we have these ferro chains, which are coupled to their neighbors anti-ferromagnetically. Now, one of the things that you learn in physics, you learn particularly in spin systems, is that very frequently the variables that you're given naively are not the easiest variables to analyze the system. And that's appropriate here, true here as well. So the simple variables, the naive variables, if you will, are spin flips. And so we think about excitations in the system, we can think about flipping spins, and that's of course an excited state of the system. But point is that it turns out to be more useful to concentrate not on the flip spins, but on these blue dots, which are the domain walls between one ferro region and another ferro region. And one of the things that you can see happens here in the language of the blue dots is this anti-ferro interaction between the two, between the neighboring chains works as a linearly confining potential on the blue dots. Now, if the system was pure Ising, that would be the end of the story, but it's not pure Ising. There are these other interactions in the system, which look a little bit like transverse field terms that serve to flip the spins. And in the language of spin flips, the spin flips are spin flips. But in the language of the blue dots, spin flips are tunneling terms, right? So if I flip this spin right here, then the blue dot moves. And so tunneling is really just a version of kinetic energy in this sense. So I have a linearly confining potential, and I have a kinetic energy term. And so I can map this system to a one-dimensional Schrodinger equation where I have a kinetic energy term, and I have a linearly confining potential. If this was x squared, we would just solve it in terms of our old friends Hermite polynomials, but it's not x squared, it's x. And so we have to solve it in terms of our new friends, a class of special functions called Airy functions, where the energy eigenvalue structure has this form here, where there are these z sub j's, which corresponds to the negative roots of Airy functions. Airy functions is just some class of special functions, and there's some universal numbers that are given to it. This was all pointed out how this could work in this paper of Physical Review D by McCoy and Wu in 1978. Physical Review D is the particle physics journal. The reason why people were interested in these kinds of things in the context of particle physics is this linearly confining potential has some resemblance to the linearly confining potential, let's say, of two quarks in a meson. So we'll come back to this analogy in a moment. Now, the experiments we're doing are time domain terahertz spectroscopy. So I don't want to talk about the details too much, but this is some techniques that have been developed over my group over the past number of years.
I'm not going to help you that much this game.
Please turn off your microphone. Mute yourselves, please. It's I don't want to get into the details of how these experiments are done, but let me just say that we use this ultra-fast laser, which in this plots here is the red lines propagating around the table, goes through some beam splitters. The ultra-fast laser is incident on a terahertz emitter, which let's say passes through a sample, which could be placed at this point and falls on a receiver at this point right here. And again, if you're interested in all the details of this, I can go into it in excessive detail. But essentially what happens is we produce this essentially picosecond pulse of radiation. Inverse of a picosecond is a terahertz. And so this pulse, which is essentially a picosecond long, has all of this information that has all this spectral content, which is useful for us. Generically and historically, it has been very hard to probe materials in the terahertz part of the electromagnetic spectrum. But with techniques like this, we can do it very well. Many times we have materials, let's say, which have interesting electric degrees of freedom. But if a material is, let's say, electrically uninteresting, it's an insulator, and it has interesting magnetic degrees of freedom, then we can use the time-varying magnetic field of the terahertz pulse to excite those magnetic degrees of freedom. And what it allows us to do is to do essentially high-frequency, broadband magnetic spin resonance, electron spin resonance, electroparamagnetic resonance, if you will. Okay. Okay, that's what actually data looks like. I think in the interest of time, I'll just skip through that and show you the first spectra. So this is a plot of the spectra. It's essentially the susceptibility, magnetic susceptibility, as a function of frequency. You can see in the terahertz range, which is also corresponds to a few millieV. This is the different susceptibilities offset at different temperatures. And you will recall when I showed you that plot of the heat capacity, you saw that the curve of cobalt niobate and zinc niobate started to spread something around 20 degrees Kelvin. Around 20 degrees Kelvin, we start to develop these one-dimensional correlations along the chain. And those correlations get longer and longer. And you see that the susceptibility kind of develops this kind of pronounced double peak structure. You go into this commensurate ordered state, and you really just change the temperature by 0.1 degree from here to there, and just boom, all of this rich structure come out. And if you have experience in solid state spectroscopy, I spent my career as a spectroscopist, we don't usually get spectra with this much kind of detailed, rich information. It's a beautiful spectra with lots of sharp peaks. Spectroscopists love sharp peaks. We usually don't get quite so many. Let's take a look at them in detail. So that's the lowest temperature data right there. And there is here, again, this is the absorption as a function of frequency. There's a series of peaks, M1, M2, M3, all the way up to M9. Then there's a peak which is kind of out of that series. And then there's this kind of broad blob here, which we call the M1 M1 Continuum. So let's look at those in detail separately. So first, the lowest 9. This is the energy versus some index, M1, M2, M3, M4, all the way up to M9. And there is the model of McCoy and Wu that they wrote down in Physical Review D in 1978, based on this Airy function solution, the continuum solution, if you will, to the Ising model. We can fit the whole discrete spectrum with just 2 free parameters. It is, I think, remarkable that in a material system that if you will, could have started its life blown out of a volcano, that all of this rich structure is present, which reflects these special functions, these Airy functions in this regard. Okay, those are the lowest 9 peaks. There's other peaks as well. And there was, again, this 2M1 and what we call M1 plus M1 continuum here. And this is where this quark analogy is useful. We know we don't have such a thing as free quarks. If we have a meson, let's say, and we pull on the quarks in the meson, eventually we put enough energy into it that it's more energetically efficient to break up this system not into free quarks, but you pop new quarks out of the vacuum and you're left holding 2 mesons. And essentially the same thing happens here. When you hit an energy, which is essentially 2 times M1, it becomes energetically efficient to make not, let's say, higher order M states, but in this case, we're going to find that we're going to make 2 sets of M1 particles, bound state, 2 sets of M1 bound states, moving apart from each other with 0 center of mass momentum. Okay, that's this M1 plus M1 continuum. And then there's this other guy here, 2M1. And that we believe actually turns out to be, let's say in the language of quarks, a 4-quark bound state, which comes from an interaction between the spins on neighboring chains. So my colleague, Oleg Chernyshov and his student Anirban some years ago did simulations on this. And you may know or recall, let's say from elementary quantum mechanics, that every one-dimensional potential, irrespective of its shape, has at least 1 bound state. And so you can kind of convince yourself that if I have, let's say, this is just a cartoon, if I have 2 spin flips on one chain and 3 spin flips on the other, there's this kind of trapezoidal interaction between them that leads to confinement. And there's a bound state that's associated with this, and that state there, which we call 2M1, that's the bound state. So again, it's this example of the fact that every attractive potential in 1D admits at least one solution. Okay, so that story is largely about us looking at the material system when we cobalt niobate, when we cool it down to low temperature, and the very rich physics it presents. That was all essentially a bonus. You know, one of the things that we were very interested in was taking this material system, the 1D system, if you will, and tuning it with a transverse field through a quantum phase transition. So this one-dimensional Ising model in transverse magnetic field is perhaps the simplest example of a quantum phase transition, and something that we were interested in studying. So I was in my office some years ago, one fall, and when my computer beeped and I got an email. Dear Dr. Armitage, enjoy these pictures of my father for your talk, Tom Ising. So it turns out that I was giving a talk, I was actually visiting Berkeley some years ago, giving a talk, and Tom Ising, who is a retired doctor, the only son of Ernst Ising, living in Peoria, Illinois, has a Google alert set up on his name and saw that I was giving a talk. And what it struck up a remarkable correspondence, remarkable at least for me anyway, where I got to learn a lot about the history of this man, Ernst Ising. This is the picture that I'd showed you earlier, 1925. Ernst Ising was born in Cologne in 1900. And I think it's fair to say that the events of his life run parallel through most of the major events of the 20th century. He got his PhD in 1924, but he was disappointed by his, let's say, self-perceived failures in this regard. He worked for a year in a patent office, but let's say with less success than other notable patent clerks around that time, and he didn't like it. He decided to become a teacher, and he left for Berlin in 1928 to study philosophy and the philosophy of teaching. He met a woman named Joanna Eimer as a doctoral student in economics, and they were married in 1930. This is them on a camping trip on the Danube River in the 1930s. He taught in various German high schools until January of 1933, when Hitler came to power. And then Ising was Jewish, and the racial laws that were instituted meant that he was essentially unemployed for a year. This was the beginning of what Joanna later called in her memoirs, called 12 years on a tightrope. In 1934, he got a job as a teacher for Jewish children in an experimental school near Potsdam, Germany. And the school expanded throughout the 1930s due to the increasing number of Jewish children, which were admitted to it as they were kicked out of their own local schools. In 1937, he became headmaster of the school. It was an experimental school, and one might say that although terrible things were going on outside the world, it was said by a teacher of those years that it was an oasis in the desert. It was called that by a teacher, and it was described as without a syllabus, without state recognition, but with lots of freedom and lots of music. It's clear that, particularly discussing with Tom Ising, that's a picture of him right there with one of Ernst Ising's former students, that Ising cared deeply for his teaching and for his students, but also for them. Many of the students came to the United States eventually, and of course, many of them for losing much of their families. And many of them kept in touch with this older man who had taught them math and science. The connection they had was deep and long lasting. And Tom Ising had told me that he had met them many times, and one became his godmother, and they had spoke many times of the care that Ising had for his students. The Nazi threat in the 1930s was of course constant in those years, and vandalism to the school and threats to the students were ubiquitous. Ising and the founder of the school made repeated attempts to get protection from the local authorities, which these were always refused. And the official communiques say things like the state had no reason to promote such facilities, meaning this school for Jewish children. And the quote was that one can find, the applications were presumptuous. The terrible actions by the community were dismissed on the grounds that they were justified because of the popular anger of the Jewish home in Kaputh. Kaputh is the small town near Potsdam where the school was. And as the 1930s went on, the teachers prepared for something bad to happen. Betsy Rosenthal, who lives in London, is the only surviving student. And she tells that in those years, the students were always taken for many walks in the woods that she only realized many years later were to figure out various escape routes behind the schools. November morning, 1938, the Kristallnacht happened. This was this pogrom against Jewish schools and businesses in Germany. A crowd of 120 people, mob gathered in front of the school, and they were delayed by the founder of the school, and Ising and the other teachers took the students out the back. The school was destroyed and never reopened. In the early morning hours of January 27th, 1939, Ising was taken in by the Gestapo, and he was interrogated for 4 hours. He was dismissed after he promised to leave Germany. And they had plans to go to New York City. They went to Luxembourg with his then pregnant wife. They had plans to get to the United States. Ising's sister lived in New York City. But let's say, apropos of the current era and quotas for immigration at the time required them to stay in Luxembourg. In the spring of 1939, their son Thomas was born. In May of 1940, 1 year later, the Nazis occupied Luxembourg, which put them at risk for deportation. And the Isings thought for a long time that he might be deported and sent to the camps. Unbeknownst to the Isings, and after some uncertainty, it was eventually decided by the Nazis that the very last people who would be sent to the camps were Jewish men married to German women. And Joanna Heimer became Jane Ising, was German, not Jewish. And Ising was forced to work in the German army until liberation, and they essentially just outlasted the war. He was one of only 36 Jews who survived the war in Luxembourg. April of 1947, he arrived, Ising and his family arrived in New York City, and Tom Ising was 7 years old. Here, I was interested to know what Ising knew about the work of the Ising model. This is, of course, after the Ansager Revolution, which Pauli had said was the only important bit of physics that had happened during the war. Tom told me that Ising went to a conference in Boston to look for a teaching job. And at this conference, he was asked, "Are you related to the famous Ising of the Ising model?" He knew he had been out of science altogether at this point for 22 years and had no idea that his name was indeed famous. Ising did speak in later years that finding out he was quote unquote famous was helpful to find a job in physics, but it's actually not clear when Ising learned about all the developments in Ising's model. His notebooks, of which I have copies of, seem to indicate that it was only in the late 1940s and the early 1950s, where he's kind of had the time to return to physics a little bit, that he became aware of some of the work, particularly the work that was done by Ansager. I think it's fair to say that his passion in life was teaching. And in 1948, he became a professor of physics at Bradley University, which is in Peoria, Illinois, southwest of Chicago. His passion was teaching, and he would always say that a class had only gone well unless the students had laughed at least once. As a man, he liked fine arts and poetry, and he could recite classical German poems from memory well into his old age. And this was reflected in Ising's second publication, which was titled Goethe as a Physicist, which was published in the American Journal of Physics in 1950. Here you can see Goethe as a Physicist, where he discussed Goethe, this German man of letters, Goethe's approach to trying to understand light and color. Unfortunately, mostly wrong, but not Ising's work, but Goethe's work. Didn't understand what the nature of color was, but it makes for interesting reading nevertheless. There is Ising doing one of these demonstrations that we do with the bicycle wheel, demonstrating angular momentum. And here is a cartoon that I just show because I just find it funny. Somebody took that bicycle wheel and for some reason inexplicable to me, turned it into a spaghetti strainer. In 1953, Ernst Ising got his citizenship, and presumably at that time, I'm told that Ernst went by Ernest Ising, and Joanna Ising became Jane Ising. In 1976, he became an emeritus professor at Bradley University, and on May 11th, 1998, Ernest died at the age of 98, having had a long and very productive life. For her part, Jane Ising, taught economics and German in the public schools in Peoria and Bradley University. She founded the Planned Parenthood in Peoria, Illinois. She swam every day until near her 100th birthday. And in the morning of February 2012, Jane Ising died on her 110th birthday. And Tom told me that they had been planning on having a birthday party, which they went ahead anyway, a cake with 110 candles on it. This is a picture of Tom and his wife and some locals in Luxembourg and the Rue Ernst Ising, which is the small town in Mersch, where Luxembourg, which is the small town in Germany where they survived the war, where Ising is a young, this is Tom Ising as a young boy, survived the war. Incidentally, Tom Ising was a physics student at MIT in the 1950s, and he told me that not once in 4 years was he asked a single question about the Ising model. So that, again, shows how the progression of the role of the Ising model in statistical mechanics has gone on. You couldn't, of course, graduate with a physics major now without having done lots of problems on the Ising model. Okay, so I have lots more to say, and it's basically no time to say it. But in the last bit, I want to give you a feeling about the direction that we're going now and the things that we're doing with this material now. What I've talked a lot about, and of course is relevant to most of the history, is the classical case, classical aspects of the Ising model. But sometimes we've added small quantum terms. But here, now I want to make things explicitly quantum mechanical. I want to tune a system through a quantum phase transition. And what we know is that the Ising model in transverse magnetic field needs to have a phase transition. So we know that in the ferromagnetic case, let's say it's zero transverse field, that the system is twofold degenerate. As you cool down to low temperatures, all the spins can be up, or all the spins can be down. As you would put a very large transverse field on the system and eventually push the spins, let's say, pointing all in the x direction, the system will be spin polarized, and that's a singly degenerate ground state. And so you can't go from the twofold degenerate ground state to the singly degenerate ground state in a smooth way. There's a quantum phase transition. Quantum phase transitions are important objects of discussion and study in condensed matter physics, relevant perhaps to things like Cuprite superconductors, heavy fermion materials, and the Ising model in one dimension, tuned with transverse field, is the simplest example of that. Okay, in general, quantum phase transitions are characterized by a collapse of energy scales. And so what we want to kind of think about is a Hamiltonian that looks something like this, where let's say we have the spins in the z direction interacting with each other, but we put a very strong field in the x direction. When we will apply the transverse field on the system, the energy scales come down, if you will. The energy for the lowest excited state in the system comes down before finally going to zero at some point, and that's the phase transition itself. Many quantum phase transitions, and phase transitions in general actually, are characterized by what we call duality relations. A description on one side of the transition allows itself with some variable appropriate change of variables to a description of the other side of the transition. And that's true here as well, quite famously, in terms of what we call the Cramer's Vania duality. In the ferromagnetic case, in this Ising chain, there is what we refer to as this Cramer's Vania duality that relates the excitations on one side of the transition to the excitations on the other side of the transition. And here it's important to note the very different character of the excitations on one side of the transition with the excitations on the other side of the transition. The elementary excitations on the ferromagnetic side of the transition are these domain walls here, which are separating, let's say, aligned spins one way from aligned spins the other way. On the other side of the transition, when the system is fully spin polarized along the field direction, the excitations of the system are just spin flips. And if we write down, let's say, the Hamiltonian in this particular form here, where G is some kind of dimensionless magnetic field that we could tune the transition, the energy gap to make a domain wall is given by a particular expression on the ferromagnetic side, is the same expression as given on the paramagnetic side to make the elementary excitation on the paramagnetic side. There's something extra here, though. The ferromagnetic system itself is very interesting because this kind of object here, this domain wall, is, say, a very unusual non-local object. You come in with let's say, a photon to flip a spin or a neutron to flip a spin. You have to make two of these domain walls at a time. And so something that you'll find is that the excitation gap on the ferromagnetic side is 2 times delta. given some distance away from the phase transition. But on the paramagnetic side, it's just delta. And it's this factor of 2 difference, that along with, let's say, the conservation of domain wall parity in the system, it's a universal number, this factor of 2, that is a universal number like other universal numbers that we can measure in physics. And it's this factor of 2 which reflects this Cramer's Vania duality. So in the final little bit, let me just show you our evidence for that. So this is a plot of the infrared absorption. Again, a plot that has to do the quantity being plotted is the absorption, but it's related to magnetic susceptibility, here plotted as a function of frequency. And what we plotted here is a bunch of frequencies, a bunch of different magnetic susceptibilities, a bunch of spectra plotted at different transverse fields, okay? Which you can see, this is the 0 transverse field case. And so that has all of the structures in it that I was discussing earlier. We put a transverse field on the system, and you can see a few things happen. First, this spectra kind of, it's hard for me to really point out. It's easier to point out when I'm in front of you, but what you can see is that the spectra is this kind of complicated dependence, and it kind of first narrows before finally coming down in this fashion and then back up on the paramagnetic side. This energy scale collapse here before coming back up. This is the, essentially, you're seeing in the raw data, critical slowing down of a quantum phase transition variety. So many people, when they're kind of looking for quantum phase transitions, try to extract out the existence of this energy scale collapse near a quantum phase transition by doing some kind of scaling phenomena, or doing some kind of scaling relation. Really what that scaling does is extracts out this energy scale and gives you evidence for this energy scale collapse near the quantum phase transition. We don't have to do anything like this. We can just see it directly with our eyes, the energy scale collapse, essentially the critical slowing down near the phase transition. Now, when we plot this lowest energy state as a function of magnetic field coming down and then coming back up the other side, that's what's plotted right here. So this is the gap here to make. Remember, the elementary excitations are a single domain wall, but we always have to make 2 at a time in the case of the ferromagnet. So this is the energy gap coming down and then coming back up on the other side. And what you can see here is the gap coming down on the ferromagnetic side and back up on the paramagnetic side. This is the ratio of these energies is precisely very close to 2. This is the universal number that shows you the Cramer's Vania duality. And I think it's fair to say that this is the first direct evidence for this duality, as well as, if you will, the topological conservation of domain wall parity. I think that's all that I'm going to have to say. I want to say about this. I think that I probably will. Well, I have a few more minutes. I think I'll take 1 more minute to say one more quick thing about this, and that is the following. Is one of the other kind of things that you see in the spectra is that you can see that when we first put the transverse field on, the energy comes up a little bit. Whoop. When we first put the transverse field on, this energy kind of comes up a little bit. That's this guy right here. This energy is coming down. There's kind of this narrowing of the spectrum, right? And then this feature comes up. That's this guy. And this, of course, is going down to the phase transition and coming back up. This narrowing of the bandwidth for small transverse fields, this is quite unlike the prediction for the Ising model. One doesn't expect this at all. And this is where I got to in this talk at the University of Kentucky a year and a half ago, and got Ribu Kall and I to discussing. And we finally realized that this actually had to do back with one of the features that I had kind of dismissed in the early parts of this talk, and that has to do with the zigzag chain of the system. That there is in cobalt niobate, due to the zigzag chain and the fact that the Ising axis slightly changes its direction from site to site as you go down the chain. The Ising axis, if you will, has this kind of zigzag motion. In addition to the zigzag of the chain, the easy anisotropy changes its direction as you go down the chain. That this gives an intrinsic transverse field on the domain walls in the system, but has a very interesting behavior that it is this, if you will, because of the local axes are kind of alternating the sign of this angle as you go down the chain, that this internal field has an alternating sign for every bond. And so when you put on a small field in the very beginning, some of the transverse field bonds go up and some of the transverse field interactions go down, some of them get smaller. And if you will, that's what leads to this bandwidth narrowing. But eventually you put a large enough transverse field on, this system goes and eventually it's still in the Ising universality class, and it still shows this Cramer's Vania duality. This is all very important in the modern context. Those of you who are interested, let's say, in quantum spin liquids may recognize that this Ising axis, which alternates its direction as you go down the chain. This is very much what was discussed in the context of the Kitaev model, this exact solution for a quantum spin liquid. And I think it's also fair to say that in cobalt niobate, what we have is really the first definitive evidence for a Ising, a Kitaev interaction. And we call this Ising chain here, this kind of Ising chain with these modified interactions, the twisted Kitaev chain. Okay, and it brings up all kinds of interesting points about how one might be able to use cobalt ions as a possible source of Kitaev interactions. And work on this area is currently ongoing at Johns Hopkins. My final point that I will leave the last words to Ising himself. This was from Ising's, again, second paper, which was in the American Journal of Physics in 1950. As he said in this paper, Goethe's approach to science was that of an artist who thought he could conceive the secrets of nature in all their complexity. He was convinced that translation into the language of mathematics was distortion of reality. I don't think anyone on this call probably believes that the translation into mathematics is a distortion of reality. In fact, what I think we see that there's something very, very beautiful with realizing things like perfect exponents and universal numbers, factors of 2, that could be realized near magnetization transitions, or special mathematical functions like area functions that appear in excitation spectrum of what is effectively a small rock that could have started its life blown out of a volcano. I hope I've told you and convinced you that there's a lot of interesting work here to do in systems like this, and in particular this material cobalt niobate 206. The best realizations of Ising's model is actually something that's going to keep us busy for many years to come. And we're doing lots of work on it now, really mostly investigating aspects of it and of the quantum phase transition. And again, this is perhaps the best example we have of a material system that is Ising's model, but then also the best example of a system that is transverse field, that is described by the transverse field Ising model. I've talked to you about the history of Ernst Ising and Ernst Ising and beyond, and then a number of different things about the experiments that we've done. Terahertz experiments in cobalt niobate, 9 meson bound states, and this first, I think, experimental demonstration of Cramer's Vania duality and Kitaev interactions. So I think that's it. That's all I wanted to say. I thank you very much for your attention, and I'm happy to take any questions.
Great, thank you. Let's give a big round of applause to Peter. Questions for Peter? Hi, Mike.
Hi, Peter. Thank you very much for your great talk. I have a question about the Cramer's.
Who am I talking? Sorry, who am I talking to? Oh, I see. There you go. Got it, Jeff.
I have a question about your Vania Cramer's duality figure. So I see on the left you have the data, and on the right seems to be the expectation that you're trying to map to. But I got confused because the axes were, X and Y axes were a bit flipped. And then when I look at the...
On this plot here, you mean?
I think you're not sharing.
Oh, I'm sorry. Yes, I'm not sharing. Let me do that. I stopped sharing for a moment. Am I sharing now? I'm sharing now, right?
You're sharing now, yeah. So I see you.
Okay, I was sharing the wrong thing. Sorry, again, I apologize here. Stop share, share screen. That's what I wanted to do. Got it. And go ahead.
Oh, I don't see. Okay, now I see your slide. I guess, so I see the slowing down or the drop of the energy is supposed to go to 0, but the data seems to go to about half of a milli eV.
You mean as it comes down here?
Yes.
Comes back up? Yeah, so all spectroscopies are limited. They have a spectral range in which they work well, and we would love to follow this all the way down to the lowest energy scales. That's something we might be able to do, and we're trying to do to really look at the details of how this all works using various kinds of microwave spectroscopies at the lowest temperatures. But in this case, we can follow these plots down to some point, and then we just can't go below that.
I see. And then I see you have an additional feature from 0.6 terahertz to 1 terahertz.
Up in here, yeah.
Or the one below it, or which one of them? How does it show
This here,
up?
you mean?
Yes.
Yeah. So there's a lot of details here which I didn't discuss. And so one of the very interesting things about this is that so the system has the zigzag chain. When the system has its zigzag chain, it also has, and this has been discussed a little bit by a very nice theory paper of Sid Parameswaran, that there's a glide symmetry in the system. So even though the system has a zigzag chain, and every bond, if you will, has a kind of internal transverse field, which has the opposite direction, you can't actually, there's no physical manifestation of that. This symmetry that is present there, that glide symmetry, is broken when you apply the transverse field. Now, not every bond is the same anymore. And so what this has the consequence of is that you actually end up having, I don't think I have the plot here handy, but it's in our paper if you're interested in the details. But you actually end up taking this kind of broad bandwidth of which, and when you put you basically double you have the Brillouin zone size, you form gaps at the Brillouin zone boundaries, and there are new optical excitations that you weren't able to make previously. There essentially end up being a lower band of spin-ons and an upper band of spin-ons, and you can make a spin-on pair or domain wall pair by having 2 in the lower band, 2 in the upper band, or 1 in the lower and 1 in the upper. And that is what gives rise to kind of all of this rich structure in here. This is, again, it's a very beautiful demonstration, I think, of universality, that you do have all these other details, and very interesting details that we want to understand, but ultimately they don't matter for the lowest energy physics. This is still in the Ising universality class, and you still get this universal factor of 2.
Thank you very much.
Yeah, you have a question. Yeah.
Peter, that's a wonderful talk. Thank you. So I have a question where I think I know the answer, but I just want to hear it. So at the end of the day, this is a highly anisotropic antiferromagnet below some critical temperature. And the fundamental excitations, the elementary excitations, I would anticipate would be some sort of spin wave. And so the sort of the mapping that you have must be sort of above some energy scale, and maybe in a way that's also your answer to Bai, which is the energy scale that happens on is below where your resolution is, and at higher energy scales, this maps onto this simpler model. But I just wanted to make sure I was seeing that correctly.
Yeah. So so thanks for that. So it's a little bit of a matter of terminology. So if we have as you presumably know, so if we take the simplest case of a magnetic system, which has some kind of, let's say, rotational symmetry, then because of this rotational symmetry, we'll know that angular momentum is quantized in that direction. And we have all these various excited states that we can have in the system that correspond to eigenstates of the angular momentum operators. So the lowest ones are typically magnons. But you can imagine a situation where you have let's say, and that's a spin flip, some kind of delocalized spin flip as a magnon. I know you know this, I'm just giving background for everyone. But there are other excited states in the system. Well, you can have 2 spin flips, 3 spin flips, 4 spin flips, 5 spin flips. We don't usually see those in spectroscopy because we don't have any way to couple to them, right? You can't go from no spin flips to 5 spin flips because there's no neutron or photon-like object that allows you to make 5 at a time. In this particular case, and let's say, take the case where I had this system I didn't put the transverse field on, but I had this M1, M2, M3, M4, M5, and 9. So in a system like this, it has sufficiently low symmetry that the energy eigenstates of the system are not also angular momentum eigenstates, are not angular momentum eigenstates. And so those excitations are actually mixtures of different amounts of spin flips. So, and how much is mixed in depends upon the strength of the confining interaction. And so the lowest state, which I called M1, is mostly one spin flip, but it's a quantum mechanical admixture of 2 spin flips, 3 spin flips, 4 spin flips. I might actually have a plot here for this. Let me just flip through my slides. I have a plot of the wave functions for these simulations we did. And I don't seem to have it. That's okay. But the point is that all of that M2, M3, M4, and 5, they're different numbers of spin flips mixed in. So by the time you get to M9, it maybe has the expectation value of, most likely it has 7 spin flips in it, but it has admixed into it a little bit of 1 spin flip. And that's what you couple to, which allows you to see it. So the point is that angular momentum, that the system doesn't have these rotational symmetries. So the energy excitations are not angular momentum eigenstates. And so you have this plethora of different excited states that you can access, even though effectively what the photon does is only ever flip a single spin. But a single spin flip projects onto many different kinds of excitations, and that's how we see them. If you really turned up the kind of the coupling between chains, so what I said was we have a very strong ferrocoupling and a very weak anti-ferrocoupling. If you turned up that anti-ferrocoupling, so it was of the same order as the ferrocoupling, then essentially what you would do is what I was saying, that the way we should think of these is basically confined domain walls. But this confinement would be so strong that the domain walls would only be 1 spin long, and that's essentially a magnon.
Okay, thank you.
Yeah.
Okay, other questions for Peter? Okay, in that case, I have a sort of related question, but not directly. Peter, it's clear that you have an interest in history of science. I have a question. What happened to the Shockley papers?
Oh, the Shockley papers. Yeah. So that's an old story there.
You gave back to Stanford?
I gave them back to Stanford. Yeah.
Okay.
Yeah. So I guess I have to tell the backstory to this. When I was a graduate student, he didn't mention it, but I was the ex-graduate student. And graduate students get to do all of this nice research, but essentially they're asked to do other things too. And I guess you guys are all in the renovated McCullough building, but at that time McCullough was not renovated; it was just was being renovated, and all of the stuff from the Shen lab had been sent to a storage area in San Jose. ZX's group had a lot of overlap with a guy named with a now deceased professor, Bill Spicer, who was one of the guys who turned let's say the photoelectric effect into photoemission spectroscopy. And a lot of this stuff so ZX asked me to go down to San Jose and look through the storage area, which was all of this old Spicer stuff. And in one of these they thought we should just throw it all away. And one of these old filing cabinets that I was asked to look through was a big fat folder that said Bill Shockley on it. And Spicer and Shockley were I don't know, Spicer, I asked him about it. He said they weren't actually friends. Shockley, of course, the father of the transistor, but also had a rather odious history as somebody who was also a exponent of eugenics and kind of forced sterilization of people and all of these kinds of things. At any rate, there was a big thing of original correspondences of Bill Shockley with essentially with Spicer that Shockley had sent him, and a lot of people were still alive at the time. I didn't know what to do with all of this stuff. I took it home, held on to it for 20 something, well, I guess 15 years. And after everybody had passed away, it's now sitting, I think, in the Stanford archives. Sent into the archivist at Stanford. They were happy to get it.
Yeah, that's sort of one of the evidences they were competing for where the Silicon Valley started, is in San Antonio Road or in Palo Alto. So.
Yeah. So there was all of this. Mostly this was in Shockley's later years, and it was unfortunately less about the founding of Silicon Valley and was more about Shockley defending his views on kind of the intrinsic supremacy of races and forced sterilization. So it was not but that's a bit unfortunate, but it's all a part of the history. And I think the Stanford Archives maintains a big collection on Shockley. And now they have a bunch of original papers which would have been thrown in a dumpster.
Yeah, thank you for rescuing that, at least for good, for bad, that the record being kept. Okay, other questions for Peter? Okay.
Yeah.
All
Anyways, thank you very
clear.
much.
Thank you so much for giving the talk. We hope to host you next year.
Yeah. Okay. Yeah. Thanks very much, everyone. Take care.